Okay, I'd like to pick up where we left off last time and finish section 5A. The last topic that we have to talk about in 5A is chemical potentials of liquids. And a quick note on notation. Going forward, a star superscript is going to indicate that we're talking about a pure substance, so that we can differentiate between pure substances and mixtures. Okay, so let's imagine that we have a box that contains a substance A, pure substance A. And some of this is in liquid form, and some is in gas form. And these two things are in equilibrium. So up here in the top portion, we have a chemical potential of substance A. And since it's a pure substance, I'm going to put a star. And that's the chemical potential of the gas. And down here we have the chemical potential of the liquid. And if these are in equilibrium, then that implies the chemical potentials are equal. Okay, and we just saw that for a perfect gas, we can write the chemical potential. We have a formula for it. The chemical potential of a perfect gas, in this case, substance A in gas form. And it's a pure substance, so I'm going to put the star here, is equal to the standard chemical potential at standard pressure plus RT, natural log of the pressure of gas A. And again, it's pure A, so I'm going to put a star here. Now, if we take this quantity and we plug it in up here, we get a formula for mu A, liquid. So mu A star liquid is equal to mu A star gas. So it's equal to this formula that I just wrote. Okay, so that's for a pure substance. Now let's talk about a mixture. Okay, so now we're going to add a solute, B, to substance A. Okay. And just as an aside, when I say solute and solvent, what we mean here is that the solvent is the component in the greater amount, and the solute is the component in the lesser amount. Okay, so if we're calling B a solute, then we're basically implying that there's not as much B as there is A. Okay, so we add the solute to A, and we still have our box, but now it has a mixture in it. And there's going to be a liquid portion and a gas portion. So now we have liquid substance A plus liquid substance B down here. And up here we have A gas plus B gas. Okay, so I want to focus on just A. So focusing on just A, here we have the chemical potential of A, gas. And here we have the chemical potential of A, liquid. And notice I've dropped the stars because this is no longer pure A. It's a mixture of A and B. And I'm looking at the chemical potential of just substance A as it exists in this mixture. Okay, so we can follow the same argument that we just used to show that the chemical potential of the liquid A is equal to the chemical potential of the gas A plus RT ln the pressure of A. We've dropped the stars because we're no longer talking about a pure substance. And this pressure of A here is going to be the partial pressure of A. Since it's part of a mixture, there's also, B is also going to have its partial pressure. Okay, so I've put the previous equation right here. This is for the pure substance. And then I have this equation for the, I forgot my standard symbol. I have this equation for the mixture. And notice that these equations both contain this term, standard chemical potential of A in gas form. So we're going to use that to substitute one of these expressions into the other. Right? So I'm going to start with this first expression up here. I'm going to rearrange it by solving for this factor that also exists in the other equation. And once I solve it for this, I'm going to take the result and I'm going to plug it in to the second equation. Okay, so rearranging the first equation, solving for the standard chemical potential of A, I get this, and I've labeled this equation star. Let me label this one asterisk, asterisk, okay, double asterisk. And so now we're going to insert that result here into the second equation, the double asterisk equation. All right, so I've just basically rewritten the second equation here, and now I'm going to plug in this right here. Okay, so the right-hand side is going to become this, which is the mu A standard, plus this term. And here I have an RT-ln and an RT-ln, so I'm going to combine those. So this is going to end up being RT-ln PA divided by PA star. Okay, so here we have the formula for the chemical potential of a liquid A that's in a mixture with another substance B. Now let's focus on this PA over PA star term. So after a series of experiments, a scientist named Raoult found that PA over PA star is roughly equal to, experimentally, he found that it's roughly equal to XA, which is the same XA we've seen before, the mole fraction of A. So some number between 0 and 1, the percentage of the mixture that A accounts for in terms of moles. So with this, if a mixture obeys Raoult's law, we call it an ideal solution. So an ideal solution obeys Raoult's law. And we'll see in just a minute that not every solution is an ideal solution. Not every solution is going to obey this law. But if we take Raoult's law here and we put it into our formula up here, this PA over PA star just becomes XA. Okay, so using Raoult's law, we can write this expression up here for the chemical potential of a liquid that's in a mixture as mu A star, that is the chemical potential of the substance in liquid form when it's pure, plus RT ln of the mole fraction of A. All right, so this is the chemical potential of A in an ideal solution. All right, what does it mean for Raoult's law to be obeyed? So if we look at this equation for Raoult's law, and I rewrite it as P is equal to P star times XA. All right. This is a constant, and therefore this, if I were to plot this PA versus XA, I should get a straight line with a slope of PA star. So if I compare this to y equals mx, I should get a straight line. So if I plot PA versus XA, and I get a straight line, then that is an ideal solution. So Raoult's law is fairly closely obeyed by mixtures of two similar liquids. So for two similar liquids, we will see that Raoult's law is followed pretty closely. Okay, and what do we mean by similar liquids? We mean that they have a similar chemical structure. Okay, so let's do an example. Okay, for two similar liquids, your book uses benzene and methylbenzene. So what I'm going to do is I'm going to sketch the experimental data. If we look at pressure versus the mole fraction of the methylbenzene. Okay, so when we have pure methylbenzene, the pressure is about 30 torr. And as I decrease the mole fraction of methylbenzene, experimentally we get a nice straight line here. So methylbenzene is following Raoult's law. Benzene, if I have pure benzene, that means I have zero methylbenzene. So pure benzene would be on the y-axis here. And in that case, I have a pressure of about 80 torr. And this one, again, follows a nice straight line. Okay, so both of these are following Raoult's law pretty well. Notice, of course, that the pressure of benzene, when there is zero benzene, it has zero pressure. And when methylbenzene has 0 moles, it also has 0 pressure. Then the sum of these two straight lines is going to be another straight line. Here it's 80 plus 0. Here it's 30 plus 0. So it's going to, the total is going to be 80 over here, 30 over here. So if I connect these 2 points with a straight line, this is the total pressure of the mixture for various mole fractions of methylbenzene. Okay, another example, this time for dissimilar liquids. The textbook uses carbon disulfide and acetone. Okay, so once again, I'm going to plot the pressure versus the mole fraction. In this case, I'll put the mole fraction of carbon disulfide on the x-axis, pressure on the vertical axis, and torr again. All right, and now I'm going to sketch the graphs for these two substances in mixture based on experimental data. Okay, so we get something that looks like this. And you see that these lines are not straight. So these, this mixture, these substances in this mixture are not following Raoult's law. However, I want to point out that it is fairly linear. CS2 is fairly linear over here. And what's special about this section over here? Well, this is where CS2 makes up the majority of the mixture. So when CS2 makes up most of the mixture, it follows a pretty straight line. Acetone, when CS2 makes up very little of the mixture, acetone makes up most of the mixture. And here we see that acetone also is fairly straight when it is the majority in the mixture. So I'm going to summarize all that in text here. Okay, so these are not linear. So this is not an ideal solution, this mixture between these two substances. But it is fairly linear when one component or the other makes up most of the molar fraction. As I mentioned earlier, if a component makes up most of the molar fraction, then we're calling that the solvent. So Raoult's law is a good approximation for solvents when the solution is dilute, so that the solvent makes up the vast majority of the mixture. Raoult's law is a good approximation. Okay, so the conclusion we can draw here is that Raoult's law is a good approximation for a solvent in a dilute solution. So that's a useful statement about the solvent. Let's focus now on the solute. Okay, so William Henry did a series of experiments focusing on solute. And in the process, he came up with this relationship, which is called Henry's law, which is that the pressure of substance B is a straight line, roughly, if we plot it versus xb, but the constant, the slope, the constant proportionality here is some other constant, which is called Henry's constant. And it varies from substance to substance. And the way that you find Henry's constant is that Kb is equal to the slope of P versus X when X is 0. Okay, so I think this is easiest to understand if I draw it. So I'm going to plot P versus X for a solute B that's dissolved in a solvent A. Okay, so here's a sample plot of P versus X for a real solution. So let me label this one real solution. Now, Raoult's law, we just talked about, is basically assuming that this has a straight line behavior. So if I take the endpoints of this line and I connect them with a straight line, that is Raoult's law's prediction. All right, that's what we call an ideal solution. So you see that this solution is not ideal, it doesn't follow this line. And what Henry's law says is if we take the slope of this line when the mole fraction is 0, so that's over here at the origin, if we look at the slope of this P versus X line and we extend it, then this is Henry's law prediction. Okay, so it turns out that both of these are useful if we can use them at the same time. And if we can do that, we call this an ideal dilute solution. Okay, so when is Henry's law a good approximation? It's a good approximation over here, close to the origin, where we have relatively small amount of the substance B. Okay, so Henry's law is a good approximation for the solute in a dilute solution. And as we pointed out before, Raoult's law is a good approximation for a solvent in a dilute solution. So we have this combining the two. If the solvent obeys Raoult's law and the solute obeys Henry's law, then we have a special name for this. We call it an ideal dilute solution. Okay, so let's do an example. Let's do an example that has acetone and chloroform in a mixture. So I'm going to call acetone, I'm going to denote it with an A, and chloroform with a C. And first, let me write down, I'm going to write a little table of experimental data. Okay, so here's some experimental data for a chloroform acetone mixture. And I'm not going to plot this, but if you want to see a plot, it's in your textbook on page 153. This data is plotted. What I want to do is I want to find Henry's constant for each of these components. So how are we going to do that? Remember, Henry's constant is the slope of this line close to the, well, I shouldn't say the origin. It's the slope of this line close to where the mole fraction is 0 or close to 0. Okay, so for chloroform, when is the mole fraction? So this is the mole fraction of chloroform up here. So it is 0 here, and my next data point is at 0.2. Okay, so 20% mole fraction, and I have this partial pressure. All these pressures are in kilopascals. So can I find the slope? I can. So so here's how we find Henry's constant. So I want the slope. I'm going to use these first 2 points because that's the best that I have in this data. These are the 2 points that are closest to, I need 2 points to get a slope. And these are the 2 that include a mole fraction of 0. So Henry's constant for the chloroform, Kc, is going to equal the slope of between these 2 points here. So it's going to be delta y over delta x. So remember what I'm plotting here. I'm plotting p versus x. So p is delta y. So, or p is y. So delta y is going to be 4.7 minus 0. And delta x is going to be 0.2 minus 0. And we put this into a calculator, and we get 23.5 kilopascals. So that's Henry's constant for the chloroform in this mixture. All right, let's do the same thing for the acetone. So it's going to be the slope when the mole fraction of acetone is close to 0. So we didn't write the mole fraction of acetone here, but we could because this is a binary mixture. So the mole fraction of the 2 should always add up to 1. So this would be 1, 0.8, 0.6, 0.4, 0.2, and 0. Okay, so we want to look at the values of the pressure when it's close to, when XA is close to 0. So I'm going to use these 2 points right here. So these are my X values, and I'm going to use these 2 as my Y values. So this is a little tricky because now X is increasing from right to left. Okay, so that means when I do delta Y, I'm actually going to take the number on the left, because that's the second number. If I'm going right to left, this is the second number and this is the first number. So it's going to be 4.9 minus 0 is delta Y. Again, it's because I'm going from right to left, calculating the slope right to left. We're not used to doing that. We usually are accustomed to calculating the slope when X is increasing from left to right. And then the delta X is, again, 0.2, like it was before, because all of our points are spaced 0.2. And this works out to 24.5 kilopascals. So that's how you find Henry's constant.